everybody. So, today we are going to talk of the consequences of special relativity. I'm sure this portion is not new to you, but we'll talk of the Doppler effect in light. The prerequisite for that is, of course, a bit of time dilation, things that we have covered earlier. Well, I'm sure you've heard of Doppler effect in sound. Let's see what it is there in light when we talk of electromagnetic waves, example light. Okay, and after that we'll check, or rather we'll see whether the mass of a body actually, whether it varies with velocity. We might have heard of such things, but let's see where it comes from. Okay, so let's first of all consider, we consider a light source, and then that's emitting light of a certain frequency. Let's call that frequency nu zero. Okay, and you have an observer here. I show it by O here towards the right of your screen. I mentioned that with Doppler effect in sound. I'm sure where instead of this light source, you will be having some source which is emitting sound, okay, which is making some noise, and then emitting certain frequencies, and then it's all fine when they're at both the observer and the source is at rest with each other. But what happens if all of a sudden one of them starts moving? Okay, so let's say the one of the source start moving, and then the observer starts moving. Well, if you have the observer starts moving towards the source of the sound, don't you feel that the frequency of the sound that you are hearing has increased? It's more like a car coming towards you, and the car blows its horn. Then the more it comes towards you, you find the pitch of the sound increasing. Well, so what is it with light? Do we observe the same things, or is it a little bit different? Let's check that out. Of course, need to mention the very beginning. So, for propagation of light here, you don't need a material medium. Of course, it can propagate through vacuum. But for sound, of course, you need a material medium. Okay. So that's what we do. We consider a light source which is emitting light of a certain frequency. That's nu zero, and then we have an observer. Okay. Now, what we can also do, you can also consider this a light source, as a clock that's ticking like this, tick, 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 and then at each tick, each one of these ticks, okay, and it's emitting a light wave. Okay, so it's so what you're considering a light source as a clock, in a sense that is ticking nu zero times per second, and so on each tick it's emitting a wave. Okay, so it's now why do we put all these clocks and things here? Then because if you put these clocks, time dilation, you can make the correlation, and then we can use all the principles of relativity that you have learned earlier. And now let's see what happens if you have the source here, you have the light source which is emitting a certain frequency, and the observer starts moving. Now we can have three situations here. Either the observer is moving transversely or perpendicular to the direction of these light waves, or it's moving towards the light source, or it's moving away. So let's consider each of them one by one. Okay. Okay. So case number one. So in this, what we have is that the observer, that's we denote by O here, and it's moving uniformly with a certain velocity v, okay, transverse to the direction of the light waves. Okay. Now, if you are, in the frame of the light source itself where the things are at rest, okay, and what's the proper time in the sense between the ticks? You consider the light source to be a clock which is ticking, and each of these tick it's emitting a light wave. Okay, so what's the proper time here? Let's call it t0. Then how is it related with the frequency? Well, frequency is in hertz and time it's in seconds, so it's 1 by nu 0. Okay, so that's the proper time interval between the ticks light source frame. Okay. Now, what about how would the observer then find this time to be? Okay. Now, in the frame of the observer, the time elapsed between two ticks would be t. Now, t will not be same as t0, which was the proper time, remember, but t will be t0 divided by root over of 1 minus v square by c square. Okay. It is this very simple time dilation formula that we have used here. Okay. Now, what would then be the frequency of the light as observed by the observer? Well, you take just the inverse of the time here. Remember, this time is the one measured by the observer in his or her frame. Okay. So, let us call this frequency as nu t. It is going to be 1 by t, and then you know what 1 by t is. You are going to just see in the previous paragraph. So, you will see that it is root over of 1 minus v square by c square whole divided by t0. Now, t0 is also related with the frequency at which the light is being emitted. Okay. So, you see that, so nu t, that is the frequency as measured by the observer, that will be nu 0 times root over of 1 minus v square by c square. Now, since v is always less than c here, okay, it is going to be vt, or the since the velocity of the observer is always going to be less than the velocity of light. Okay. So, what you find as nu t, that is the frequency as measured by the observer, will always be less than the proper frequency. Okay. Proper time interval and the proper frequency, if I can put it that way. So, nu t here is less than nu 0. So, that is the frequency that will be measured by an observer who is moving transversely to the source of light. Okay. So, that leaves us with two other cases, one in which the observer is moving towards the light source, and in the other when the observer is moving away from the light source. Okay. So, let us consider the other one first, namely the one in which the observer is moving away from the light source. Okay. So, here too, what is the proper time between ticks? It is going to be 1 by, well, it is t0, which is like 1 by nu 0. That is when nu 0 is the frequency at which the light is being emitted at the source. Okay. And remember, here the observer is moving with a velocity v away from the light source. So, in the frame of the observer, if t is the time that small t is the time that the observer will measure between each of the ticks, so as to say, then for in time t, remember, the observer is also moving with a certain uniform velocity v. So, the observer has already travelled vt, that is the unit of distance here, away from the source between the ticks. Okay. So, this implies that the time interval between two successive ticks as measured by the observer, okay, will be what? Will be Vt. By how much will it increase? Will increase by Vt by c, where t is the time as measured by by the observer here, right? And Vt by c, and c is the velocity of light, and that has the same so the value of c is going to be the same in both frames. Okay. Now, what will be the total time between the arrival of successive waves or the successive light waves in the frame of the observer? It will be first the time between two ticks as measured by by the observer, plus the amount of time the observer has moved away, in a sense by which time the observer has already moved by a certain distance between these two ticks. Okay. So, the time elapsed between the arrival of successive waves will be capital T, which is small t plus Vt by c. Okay. Now, you simplify this as t plus, and then you take a bracket of 1 plus v by c. Okay. Now, how is t related with the proper time? Small t, that is, small t is related with the proper time t0 by small t being equal to t0 by root over of 1 minus v square by c square, and then you have the bracket 1 plus v by c. So, that simply simplifies to the one given at the bottom of your screen, that is t0 into root over of, so 1 plus v by c divided by 1 minus v by c. Now, how will you find the the frequency here? It's that all you need to take is the inverse of the time interval in this case. You see here I've put it as v nu minus, so that is 1 by capital T. Now, that you just invert the expression that you see in the top of your screen, and then you relate T0 with the frequency, that is the frequency with which the light is being emitted by the light source, and then you immediately find what is a nu minus. Okay, and then you can relate nu minus to nu 0, and then you see that nu minus is actually less than nu 0 here. Okay. So, in every case you see that the change in frequency, so far we have seen that it is depending on the velocity of the observer, okay, the velocity with which the observer is moving away from the light source here. Okay. So, what about the last case? So, in this case, let us say the observer is moving towards the light source. Okay. So, so by the same logic which we had applied earlier, the observer travels a distance which is v times small t towards the light source between successive ticks here, successive ticks of the clock that we have considered here. Okay. So, the total time interval between the arrival of successive waves here, light waves here, would be that is the capital T, would be small t, and then remember it is minus Vt by c. Okay, why minus? Because the observer is moving towards the light source, and then we have kept the velocity of light is the same in both frames. I mean, whether you are in a moving frame, uniformly moving frame, or in a rest frame. Okay, so that is why it is the same c. So, it's natural now. So, you do the simplification. You you convert the small t into t0, t0 being the proper time. Okay, and here what you will find is that when you take the observed frequency, when you find the observed frequency, it's going to be, if I put v nu plus here, that's nu plus is 1 by capital T, and you're going to see that nu plus here is more than nu 0. Okay, it's going to be more than the frequency of the emitted light. Okay. So, we have studied 3 cases in which the first case the observer was moving perpendicular to the light source, okay. Then the one was moving away from the light source and then towards the light source. However, I should also mention here that in all cases you have seen that in all these cases the shift in the frequency as observed by the observer, okay, depends on the velocity of the observer here. Okay, so you do see it in all these formulae here. Another important point that I should mention here is that in each of the formulae that you have seen so far, I have always considered the light source to be at rest. Why? Because had I not, for example, the light source was moving and then the observer was at rest, okay, that would have been a similar situation, because it is the relative velocity which is important here, unlike the case of Doppler effect in sound. Okay. So, it is not only in the Doppler effect in sound, it is not the relative velocity, you have to take into consideration the velocity of the speed of the source and the speed of the observer here, but here what we have, it's the relative velocity of between the observer and the source, which is going to be important here. So it's if the source is moving or the observer is moving, it doesn't matter, as long because the velocity that we are considering here is actually the velocity v that you see in all the formulae will always be the relative velocity. Okay, so having done this, let's spend a couple of minutes on where possible applications of this derivation would be. Okay. Well, as I told you, you see in the shift in frequency is related with the relative velocity with which the object is moving. Okay. So that immediately told people that maybe it could be used to measure the speeds of distant stellar objects, okay, like stars. So what do people do? What do astronomers do in that case? What they do is that they take a photograph of the spectra of elements which is in the star. Okay, so from the light which is emitted from the star, the light spectra is analyzed. So where the frequencies are, people find out. Okay, and then they compare it with the known spectra of elements present in the star. Okay, so these known spectra of elements, so you can find the spectra of elements by some experiment in the laboratory here on Earth, and then they compare that spectra with the spectra that was obtained from the star. Now, if the star is moving away, or there's a relative velocity, there's a relative motion between Earth and the star there, and the star, we're going to have a shift in spectral frequency. Okay. Now, from the shift in spectral frequency, you can then find the speed of the star. Okay. So it's got lots of applications in astronomy, of course. Then many other some other discoveries were also based on this. Okay. Another application, actually a very interesting application of this, would be to measure the temperature of hot plasma in nuclear fusion experiments, or the temperature of very hot gases. Okay. Now, what they do is that, well, the principle is almost similar, to what I have outlined earlier. It's that they take the spectra of when things are moving at such high speed, so they are emitting radiation, and this radiation is analyzed, and then if it's a known gas, so from the known spectra you can find out what's the shift in the spectral frequency. Okay, and then you can relate that with the speed of the molecule or the gas which is there inside your experiment, and then if you remember your kinetic theory of gases, so from this velocity, or the mean velocity or the root mean square velocity, you can always relate that to the temperature. Okay, so that can always be done from the kinetic theory. Okay, so that will give an estimate of the temperature involved here. Okay, so we have studied Doppler effect in light as against that now as against Doppler effect in sound. Okay, and then we've also talked a bit about a few applications. Fine. So now we're going to shift gear a little bit and do something a little bit different, and go to another consequence of special relativity, and study if the mass of a body actually varies with the velocity with which it is moving. And I know that this is one of the things that many of us are rather aware of when we study physics or any of the elementary courses of science we take. Mass increasing with velocity and E equal to mc square. Okay, but all of it in due time. Okay. Now, to do this problem of whether mass of a body varies with velocity, let's start with an example. Okay, and then we'll come to a conclusion. Okay, so concentrate on the thing written down as S prime frame. Okay, So, what we have here is that we are considering the inelastic head-on collision of two identical particles A and B in S prime frame, let us say. So, what is this S prime frame? Well, it is a frame which is let us say it is moving with a certain velocity, certain uniform velocity v with respect to another frame S, let us say. Okay. Now, in it we have the inelastic collision of two bodies here named as A and B. So, they are of identical masses, m prime, both are of m prime, and they are moving with the same speed, opposite to each other, and then they are heading towards a head-on collision. This means speed is u prime here. So, we have all put primes here because to keep in to make since we are talking of S prime frame, so we are dealing with prime coordinates here. Let us put it that way. Okay, and then all these velocities u prime, they are moving parallel to the x-axis. Okay, fine. So they are identical masses also. Now, how is the same event observed in S frame? Okay, well, you have different you have in the S frame, you're going to see the same thing as some the velocities may not be the same. The velocities, although they are moving, the speeds are all the same, but if you take the modulus of the speeds in S prime frame, they are the same. The directions may be different, but the speeds are the same. But then the velocities or the speeds are not going to be the same in S frame for a simple reason. It's that you need to invoke Einstein's velocity addition formula to find what's the velocity in S frame. Okay, and you're going to see immediately that it's not going to be the same. It's just written in for your convenience towards the end of the slide. For example, if you just consider u1, so of the mass of the velocity of mass, okay, mass A rather, okay, you're going to see in terms of the S prime quantities and then the velocity v, it's u prime plus v divided by 1 plus u prime v by c square. However, if it was minus u, since it was moving in the other direction, okay, u2, that's the other the other quantity, so that's minus u prime plus v into 1 minus u prime v by c square. It's not going to be the same. Okay, so you might be a little bit confused why you've written different masses for identical masses. Okay, so in the S prime frame you had identical masses, both are m prime. Okay, but why is it that they are different in the S frame? Well, at this stage I don't know why they are different, rather I just take them to be different. So just to keep myself in conjunction with the idea that I have different velocities, okay, I don't know what's going to be the masses. So if it is, if from my relativity, from whatever I do, it turns out from all these conservation laws I'm going to invoke on, if it turns out that these masses are the same, they will turn out to be same. M1 will be equal to M2, but right now I'm going to take M1 and M2 different. Okay, let's just see what happens. Okay, so that's what we have. We have the S prime frame, and then in the S frame we are going to see what it is going to be of the same event, the same collision, how one is going to see in S frame. And remember, S prime frame is moving with a certain uniform velocity v with respect to the S frame. Okay, so on top of that, of course, on the back of my minds, we have the conservation of linear momentum in the collisional process. Well, this is rather something very sacrosanct. I mean, we are not going to violate all these conservation principles, okay, whether it's non-relativity or relativity or classical mechanics. I mean, the conservation laws are conservation laws. You're supposed to maintain them, okay. And then on top of that, we also have the total mass to be conserved. That's the total variable mass. The total mass. For example, if it is consider S prime frame, you have m prime A, and then the other mass B also of m prime. So after collision, the mass is going to be m prime plus m prime, that's 2 m prime. That's what I mean, the total mass remains conserved in the collision process in each of these frames. Okay. Okay. So what does it mean here? Well, from the linear momentum conservation, what we have in this collisional process, if you look at the S prime frame, it's very simple, it's going to be 0, isn't it? I mean, they're moving, you have identical masses, the speeds are identical and opposite to each other, moving parallel to the x prime axis. So u prime, m prime u prime plus m prime minus of u prime, so that's going to be 0. So momentum, so even if the, so that tells you that if you're going to have an inelastic collision in the end, so you know, the mass is going to be whatever it is, but the velocity or the it has to be at rest in the S prime frame after the collision. Well, something of that later on, but what about this, the total final mass of the combination? There's a final mass of the combination m prime plus m prime, it's going to be 2 m prime. There's nothing rocket science in that, but the only thing is that it's going to be maintained after collision. That's what I want to say. Okay, so that's what we have the thing. Okay, so just one look, one more slide to recapitulate on this collisional process before the collision. Okay, so we have the S prime frame where we have identical masses A and B. Okay, they have similar masses, they have the same mass m prime and they are moving opposite to each other parallel to the x prime axis. And then one is observing the same thing from the S frame, and then the S prime frame is moving with a certain velocity v with respect to the S frame, and from the S frame you are going to see the same collisional process, but then the velocities are not going to be different. And then we have taken different masses here. We don't know whether the masses will be same or different, but let's see if from all these conservation laws what turns out to be, whether we have indeed different masses, whether m1 is different from m prime. Okay. Okay. So what happens after collision? Remember, the collision is perfectly inelastic. So what it means is the combined particles will be at rest and they will stick together in the S prime frame. So that's what they are. They will stick together in the S prime frame and the total mass is 2 m prime and they are at rest. Now, what will be the velocity with which these things will be seen to move from S frame? Okay, so is it v? We're going to find that out. Okay, but remember here, what will be the total mass of this AB system here in S frame? It's going to be m1 plus m2. Okay, because the total mass is conserved in this collisional process. Right. So what about the velocity, as we said? So remember, after collision, well, still after collision, we are still considering S prime frame to be uniformly moving with a certain speed v with respect to the S frame. Now in S prime frame, A and B is at rest, right? Is at rest. So what does it tell you? And then the S prime frame is moving with velocity v with respect to S. So what is the velocity with which A and B will be seen to be moving from S frame? Well, it's v, that's what we have. So in S frame we have these two particles, they are sticking together. Okay, since it's sticking together in S prime frame, it's sticking together, it's going to have mass m1 plus m2 and it's going to move with a certain velocity v, which is same as the relative velocity between S and the S prime frame. Okay, so just to recapitulate the entire collision process, what you see in the top of the slide is the situation before the collision, okay, both in S prime frame and the S frame. Just have a nice look on the situation what is happening in the S prime frame and the situation that we have in the S frame. Okay, that's the situation before collision, and then after collision it's a perfectly inelastic collision. So it's sticking together in S prime frame and total mass is 2 m prime and it's at rest, and then from S frame we are going to have the total mass to be m1 plus m2, the total mass is conserved here and then it is moving with velocity v. Okay. So, next what we are going to do is that we are going to invoke the conservation of momentum in the S frame. Remember, if we invoke the conservation of momentum in the S prime frame, it is going to be 0, is not it? I mean the total momentum, total linear momentum in the S prime frame is 0. Okay. And what is it if we invoke that same conservation of momentum in the S frame, what is it going to be? Okay. It is going to be m1 u1 plus m2 u2, that is the total momentum in what? In the S frame before the collision, and then after the collision it is going to be m1 plus m2 whole times v, that is the velocity with which this combination a plus b or this m1 plus m2 is moving. Okay. Now, rearrange a term, do a little simplification, so you immediately get what m1 plus m2 is. m1 plus m2 is nothing but v minus u2 divided by u1 minus v. Well, that is very simple, you just take all the m1s, you know, all the terms involving m1s on one side, all the terms involving m2 on one side, and then do simplification. Okay. And then what you do is that you substitute for u1 and u2 the expressions from Einstein's velocity addition formula. So, you know that very well. So, u1 is u prime plus v divided by 1 plus u prime v by c square, and what is u2? u2 is minus u prime plus v divided by 1 minus u prime v by c square. So, you are going to substitute these two velocities, u1 and u2, okay, in the expression given in the middle of your screen, given by this m1 by m2. Well, I'm doing a little bit of the algebra rather a little bit of the algebra. It's only, but if you miss this slide or the next, you're not going to miss most of the physics. Okay, I'm just doing it so that you will have the expression. You can derive all these things by yourselves. Okay, so what I have done is that now what will be m1 plus m2 in terms of all the quantities in the prime frame. Okay, so it's 1 plus u prime v by c square divided by 1 minus u prime v by c square. Again, what we do is that, okay, so we have derived up to the expression at the top of this slide. Again, what we see is that a little more simplification, actually you can derive this if you invoke again the Einstein's velocity addition formula. 1 minus u1 squared divided by c square, and what is 1 minus u2 squared divided by c square. So, you put in what is u1 and u2 in terms of u prime v's and all these things, you see rather very interesting expressions. You can actually check that out. Okay, it's 1 minus u prime v by c square whole square divided by 1 plus u prime v by c square whole square. Now, from the top of the slide, you can see that this is nothing but m2 by m1 whole squared. Okay. Now check what we have. Check the one on the left hand side. Okay. So, it is 1 minus u1 squared by c squared divided by 1 minus u2 squared by c squared, and then on the extreme right hand side you have this m2 by m1 in whole of squared. This is very interesting. These are the two expressions, the left hand side and the right hand side. Disregard the one in the middle. Okay. What do you see? You see the masses, you see the velocities. Okay. What do you again see? What you see is m1 into 1 minus u1 squared by c squared, and you take a square root of that, is equal to m2 into 1 minus u2 squared by c squared, take the square root of that, and that is invariant, and that is not changing. Okay. So, what you see is that what you have here. So, m1 and m2 are the masses of identical particles. Okay. When their velocities are u1 and u2 respectively. I mean, when I say m1 and m2 are masses of identical particles, and you know, does not carry much of a meaning. I mean, then you could say that identical particles, how come they have different masses? Okay. But you see that they are moving at different speeds. Okay. So, this combination, some rather interesting combinations of m1 and u1 of these speeds with which they are moving, and then that combination given by m1 times 1 minus u1 squared by c squared, that square root of that is the thing that's going to be invariant. Change the velocity, the expression for the mass changes. Okay, that's becoming invariant. Okay, so what is invariant is this combination in whatever whatever mass and then its corresponding velocity that's possible here. So what we have, so in a frame, if v is the velocity of the particle, if v is the velocity of the particle and m is its mass, then the quantity that you will have, m into 1 minus v square by c square root over of that is going to be invariant. Okay. Now this is very interesting. Why? Now what's this? Well, rather what should be the invariant quantity? Let's check that out. Now if you take the velocity with which the mass is moving to be 0, so it's basically the mass is at rest. So you consider a frame in which the particle is at rest, and then you measure the mass there. Now if the mass is m0 there, okay, so you plug in those quantities into the formula. So m into 1 minus v square by c square, so the mass is m0 and the velocity is 0. See the 1 in the bracket, 1 minus 0 square by c square and the root of that, so that's going to be 1, no problem. And then on the right hand side you have m0, so that's going to be the invariant quantity. And m0 is the mass of the same particle in a frame in which it's at rest. So that's the formula we are looking for. See that if you know that the invariant quantity is actually m0 here, you can now relate the mass of a body which is moving with a certain velocity v as m is equal to m0, which is the mass of the body in a frame in which it's at rest, and then divided by root over of 1 minus v square by c square. So what we have is the mathematical formula, and then this is very interesting, of what the mass of a body will be if it's moving with a certain velocity v. Okay. Now let's see how this is related. So let's have a graphical illustration of this variation of mass and velocity. It's if you look at the graph on your screens, what I've plotted here on the y-axis is the mass, and on the x-axis I have v by c. Okay, it's basically it's the velocity in the units of velocity of light. So it's it's starting from 0 to the speed of light. So when v by c is 1, it's the speed of light. So okay, and when v by c is 0, then you know that the body is at rest. Okay. Now if we consider a mass of which is at rest, which is m0 to be of, let's say, 10 kg. Okay. Now that's the green line. Okay, so that's the green line, and so whether if you increase the velocity or not, so that's m0, it's the rest mass, so that's 10 kg. But as you increase the velocity, okay, see the red curve. See that at small speeds, when the velocity of the body is not too high, or it's too high, not too high compared to the speed of light, you see that it's increasing, and then when it reaches towards the speed of light, you see all of a sudden it increases very fast. I mean, it's almost explodes. Okay, so you do see that the mass of the body is increasing in a certain way when the velocity is increased. Okay. Now I also wish to remind you of one more thing. It's that when you are at very small speeds, basically when you are non-relativistic speeds, okay, when v is much less than c, you can immediately figure out, look at the formula for example. Let's first look at the formula. So m is equal to m0 divided by root over of 1 minus v square by c square. So when v is much lesser than c, v by c almost tends to 0. So, the denominator in this fraction is going to be 1. Okay. So, m will roughly be equal to m0 when the velocity is much less than the velocity of light, and that is exactly what you see in the graph. Okay. So, when velocity is much less than the velocity of light, you are in the non-relativistic limit, in the classical limit, the classical world that we all live in. Okay. You see that the red line actually converges with the green line. So, it actually fits with our experience. Okay. Okay. So, now let us see. So, let's see what have another example of what the consequences of this formula would be. Let us just consider the the rest mass of an electron. Okay, the rest mass of an electron, if you look at the tables, it is something like 9.11 into 10 to the minus 31 kilograms. Now, suppose this is moving with it's a pretty high velocity, it is 80% the speed of light. Okay. So, will its mass be equal to, how much will its mass, what will its mass be? Will it be very near to 9.11 and 10 to the minus 31 kilograms? Let us see. So, that is the rest mass, and the velocity v here is 80% of the speed of light. So, what you see here will be m, so that is the measured mass, will be equal to m0 divided by root over of 1 minus v squared by c squared. Okay. Now, m0, you know what that is, 9.11 into 10 to the minus 31 kilograms. Okay. And then 1 minus 0.8 square and c square divided by c square. Okay. Now, this turns out to be something like 15 into 10 to the power minus 31 kilograms. So, you do see an increase in mass, okay, when you when the velocity is increasing, and that too when the velocity is much well, it's actually 80% the speed of light. So, it's quite a huge amount of which is it's quite a large velocity. Okay, so I hope today I have you'll be able to cover some part of the consequences of special relativity. We talked of Doppler effect in light, and then the interesting phenomenon of the mass of a body varying with its velocity. In the next section, what we will talk of is the relation between mass and energy, okay, and I will heavily draw upon what we have done so far about the consequences of relativity, especially about the variation of mass with its velocity. Well, thank you very much.